Hello, in this video I'm going to show you how to do the fundamental theorem of calculus. Now, the fundamental theorem of calculus basically starts off by looking at a shaded region of which that we want to find the area beneath a curve. So let's say that we have this curve. Let's say that we just draw it like this, and we want to know what's the area beneath it from, like, let's say A to B. And we'll just draw that the region, it lies beneath over here, and we'll just draw our shaded region. Now, you learned that probably the way that you can do this is by performing a Riemann sum, which is correct. So we know that we want to find the integral from a to b for f of x dx because that represents the area. Now, in this case, the way of which that we would do this, instead of using the Riemann sum, we would actually say that we have an antiderivative of this function, call it big F of x, and that we would be evaluating it from a to b. The next step of which that you would do this is that you would take f of b minus f of a. So in a sense, you kind of have like this top minus bottom. Okay, and this, by the way, right here, that is the area that was calculated. Okay, so if we can just find the antiderivative of f of x, little f of x, because right over here, that is what we said is the antiderivative. Okay, now the easiest way to do this is to obviously like do this by example, but before I do that, I just need to specify that there are some properties that you'll need when looking at integrals and using the fundamental theorem of calculus. So essentially we have that one of the properties states that if we have the integral from a to b of a constant times f of x dx, well, this is the same thing as the constant times the integral from a to b of f of x dx. The other property is that basically what we have here is that if we integrate from a to b, and then we have f of x plus or minus g of x dx, we have that this would be equal to the integral from f of x dx plus or minus the integral from a to b of g of x. Now, notice that you would have to still apply the fundamental theorem respectively to this function and this function over here, well, these functions, in order to figure out like what's the area for those. In a way, this is kind of helping us for finding, the area beneath a polynomial, for instance. Now, note, yeah, that we'll just say that the fundamental theorem basically says that all that we need to do is say that we have that big F of x is equal to the integral from a, so it's from a to x, and you have f of t dt. So essentially the relationship between these two, according to the fundamental theorem of calculus, is that f prime of x is equal to f of x. Okay, so this is exactly what the fundamental theorem is actually saying. But like I said, we can learn this by performing an example. So we'll look at an example. So let's say that we have the integral from 1 to 3 of 3x squared plus 4x, and this is just dx. Now we could go about finding the graph to this, but we really don't need to technically because we have that this is continuous and it's positive. So in this case, we can just go ahead and find this. So we go ahead and we say, well, it doesn't matter technically how we treat the constants necessarily because we're going to perform the antiderivative. So this would be 3x to the 3. That's going to be divided by 3, but this is evaluated from 1 to 3 plus 4x squared divided by 2, but this is evaluated from 1 to 3. Note that basically what I did here was I just tried to apply the fundamental theorem to each component technically. Now notice that you also have some cancellation, like that cancels out, that just becomes a 2. Okay, so we'll just put a 2 right there. Now what this does is it gives me x cubed from 1 to 3 plus x squared from 1 to 3. Note that we no longer deal with the arbitrary constants. So we have 3 cubed minus 1 cubed plus 3 squared minus 1 squared. So this is going to be 27 minus 1 plus 9. So we have, this will be plus 9. And then this is going to be minus 1. You know what? I forgot to put a 2. Yeah, there should be a 2 right there. So technically there's going to be a 2 multiplied by there. So that's going to be, yeah, so this is going to be equal to 26 plus, so this is going to be 16, which is equal to 42 units squared. Okay, now note that, for example, that if you were going to apply the fundamental theorem of calculus, that if you're dealing with, say, for example, you have that you're integrating from a to b, and you have that this is the velocity function, and you take the antiderivative. The antiderivative is the position function s of t being evaluated from a to b, which is actually equal to s of b minus s of a. But notice that basically when you applied the fundamental theorem, that this actually gave us displacement. So in this case, like, we can apply the fundamental theorem to applications in this sense. Traditionally, we might write actually that this is equal to, let's say, like the change in s. So same thing. Now, I can try an example where we want to find the integral from -3 to 3 of 9 minus x squared dx. But this time I actually am going to draw a sketch of the region in question. So we have that this is a parabola, which looks something like this. Okay, now it says that it's from -3 to 3, so we'll just put -3 and we'll put 3. Now, the area is bounded by the curve and the x-axis. So what that means is that the region is actually right here. Okay, well, interestingly enough, looking at this, I can tell that there's symmetry. So we have that this is equal to 2 times the integral from 0 to 3 of 9 minus x squared. And this is dx. Now, what that means is that basically we already know what the answer is because it's going to be 2 multiplied by 9x from 0 to 3 minus 1/3 x cubed from 0 to 3. But don't forget that you have to multiply by 2. So what this does is it gives you 2 times 27 minus, well, you have 27 divided by 3, which is actually 9. So in this case, this is going to give you 36. So we have that this is 36 units squared. And that's it. Now, interestingly enough, you could actually work out a similar problem where, let's say, like for example, you had two parabolas that kind of were overlapped, such as like if you have something like uh, if you have something like this, and then you have another. Well, it's not very symmetrical, but I'll just tell you that that what you would need to do is, like, let's say for example, this is y equals a squared minus so minus x squared. Well, in this case, you would say that the integral would be from 0 to a. Then you would have the a squared minus x squared. But then you would just say, well, because it's symmetrical, and try to use your imagination for the bottom part, you would actually just multiply this times 4. Because you have that there would be symmetry. So what I'm saying is that what you can do is try with y equals to 4 minus x squared and y equals to x squared minus 4. What you'll see is that basically you're just going to set up the integral where you're just integrating from 0 to 2 multiplied by 4, and then you have 4 minus x squared dx. So you could try this one and see, like, what does that look like if you graph that, or if you just evaluate it, whichever way that you want to look at it. Okay, now the last one that I'll say that you should definitely look at. Okay, so let's look at a polynomial. So if we have the integral from 3 to 5 of 2x cubed minus 3x plus 4 dx, well, again, we could go about finding the sketch of the region, but we really don't have to. So when we do this, what we'll see is that you'll end up with, okay, so this is going to be 2x to the 4th divided by 4 minus 3 halves x squared plus 4x. Now, all of this is from 3 to 5, and this is all from 3 to 5, and that's from 3 to 5. Okay, now, of course, this is going to be 1/2 multiplied by 5 to the 4th minus 3 to the 4th minus 3 halves multiplied by 5 squared minus 3 squared, and this is going to be plus 4x. Well, technically that's times 5 minus 3. Now, once you simplify this, basically what you're going to get is the following. Okay, so, well, you have to really do the 5 to the 4th minus minus 3 to the 4th. Now, that's going to be 544, but divided by 2, that's 272. So we have that that's 272 minus, okay, well, 5 squared is 25, minus 9 is 16, and then multiplied by 1.5, that's going to be minus 24. And then we have plus we have plus 8. Okay, well, that's basically just 280 minus 24, which is 256 units squared. Okay, so in actuality, it's not really that bad when you think about it. Now, you can evaluate at the very end, like say, for example, that you just plug in 5 into this polynomial, 1 half x to the fourth minus 3 halves x squared plus 4x. But in my opinion, it gets a little messy. What I did was I basically kind of grouped it and made it look nicer in this sense. Okay. Now, that's going to be it as it relates to fundamental theorem of calculus. You're just basically taking antiderivatives and you're just evaluating from the top minus the bottom. But make sure that you take the antiderivative first. That's most important. Take the antiderivative first. Okay?